I have a causal and stable system, and the statement is that I can always represent it or factor it into a cascade of a minimum phase system and an all-pass system. Now, before I kind of give you, again, somewhat of the poor man's argument, although it's more, it's cleaner than just referring to it as the poor man's argument. Yeah, let me, before I kind of give you the argument, let's just say you take my word for it. And let me ask you to think about this question. So what this question is saying is, I have a collection of systems, and each system, each of the systems has the same magnitude for the frequency response. So they all have a frequency response which is the same as the first system. But obviously they differ in the phase. What can I infer, if I can infer anything, what can I infer about the group delay? So let me ask you to think about this, and then we'll talk about where this notion of the factorization comes from. The answer is true because of what I wrote up there, which says that for an all-pass system, at all frequencies, the group delay is going to be greater than or equal to 0. So if the group delay for the all-pass system is greater than or equal to 0, then that means that the group delay of the system is going to be its smallest for the minimum phase part of this factorization. So it says something very important about how to interpret minimum phase. So effectively what minimum phase is saying is it's saying that if I give you a frequency response magnitude, and that's what I want to design against, of all the filters that I can design, causal stable filters that I can design that have that frequency response magnitude, the minimum phase one is the one that's going to have the minimum group delay. Basically, a nicer way of thinking about what minimum phase means. Let's see, I have a system function, and let's just say that the only thing that keeps it from being minimum phase is that there's one ordinary 0 that's outside the unit circle. So it's going to involve a minimum phase piece, and it's also going to have this 0 that's outside the unit circle. So let's say that 0 is at A, so it's going to look something like that. Now, what I can do is something where I can basically multiply by 1. So let me multiply by 1 by having 1 minus 1 over a conjugate, z to the minus 1, divided by 1 minus 1 over a conjugate, z to the minus 1. And let's just make a real so that I'm not worried about the conjugate. And then let's take this piece and put it over here. So this is now the minimum phase, and I'm going to multiply that by 1 minus 1 over a conjugate, z to the minus 1. And then what I'll have is 1 minus a z to the minus 1 divided by 1 minus a conjugate z to the minus 1. Well, if that 0 is outside the unit circle, so a is greater than 1, if a is real, then I now put the 0 back inside the unit circle. So this is now minimum phase. And what about this? Well, that's nothing because I wrote it wrong. This is 1 over a conjugate. And I mean, obviously, this cancels out that. I'm back to what I originally had, so I haven't done anything. But this is now all pass. So basically, what it says is it says, I have a system function, and I look at the zeros that are outside the unit circle. Well, I could also look at the poles outside the unit circle, but there aren't going to be any poles outside the unit circle because I'm telling you that I'm talking about systems that are causal and stable. So if I take the 0 that's outside the unit circle and I reflect it through its conjugate reciprocal to inside the unit circle, now I have a minimum phase system. But that's not the system I started with. So how do I get back to the system I started with? Well, I cascade that with a system that will cancel out that 0 with a pole and put the 0 back where it belongs, and that's what this system is. So that's all it involves. Now, there's another common definition or statement about minimum phase, and that is that it has the minimum energy delay property. So again, we have these h sub k's, all of which have the same magnitude for the frequency response. And so associated with that is an impulse response hk of n, and for k equals 1, it's h1 of n, and let's assume that it's h1 that is the minimum phase one. And the minimum energy delay property says the following. And again, keep in mind that we're talking about causal, stable systems. So the minimum energy delay property says that if I take h sub k and sum the values up to capital N, and so let's call this E of capital N, and N can be anything from 0 up to infinity for any value of capital N. So I'll call that E sub k of capital N, that E sub k of capital N is always greater than or equal to, it's always less than or equal to E1 of capital N for all values of n. Now, what is that saying? It's saying that I look at the h of n's, and the minimum phase h of n is accumulating its energy the fastest. So the terminology sometimes that's used is the minimum phase one is the one that's the most front-loaded. So just to kind of illustrate what's meant by that, here are 4 pole zero plots, and they all have the same frequency response magnitude. you look at this and here's the minimum phase one, because all the poles and zeros are inside the unit circle. And I'm indicating this is a fourth order pole. So that would be like z to the fourth. And then reflecting some of the zeros outside, I'll get different pole zero plots, all with the same frequency response magnitude. And if you look at the impulse responses, this is what they are. That doesn't tell you much. But here's the statement of the minimum energy delay property, which is showing how the partial energy as a function of capital N, would be the capital N that I have here, accumulates for each of those four examples. And this one is the minimum phase one. I describe this one as the maximum phase one, and maximum phase basically interpret as all of the zeros are outside the unit circle rather than inside the unit circle. And so it's saying that the minimum phase one is the one that's the most front-loaded, meaning it's accumulating its energy as fast as possible. Okay, now the proof of this is fairly straightforward. And actually, I'm not going to go through it in lecture. I'll kind of give you a sense of what the proof is, but there's a homework problem in the text that basically walks you through it.